Assalamualaikum warahmatullahi wabarakatuh. I'll present about the introduction of measurement using DC bridge. Impedance measuring bridge can be used to do precise resistance measurements. There are a number of bridges which are identified usually by their inventor's name to measure different type of resistance and impedance. For this experiment, there are two types of DC measurement, which is Wheatstone bridge and Kelvin Double bridge. The standard bridge circuit, or often called a Wheatstone bridge, which can be used to measure resistance very precisely. The Wheatstone bridge consists of four resistors, which is R1, R2, R3, and R4, that are connected in the shape of a diamond with the DC supply source connected across the top and bottom points, which is C and D in the circuit. Output is taken across the other two ends, which is A and B in the circuit. This bridge is suitable to measure medium range resistance. A DC voltage source and DC meter may be used in this case, since the impedance to be used are real. For a Kelvin bridge or Kelvin double bridge, this is a modification of the Wheatstone bridge, and it provides greatly increased accuracy in the measurement of low value resistance, generally below 1 ohm. The term double bridge is used because the circuit contains a second set of ratio arms.
Good day everyone, my name is Nithiyan. My matrix number is CE190043. So for today I would like to explain about activity 1, which is determining resistance measurement using Wheatstone bridge. So a circuit simulation, we have conducted a circuit simulation using Proteus for this Wheatstone bridge. So the circuit is shown in figure 5.2 with R1, R2, R3, which is a variable resistor, and R4. So for R4 is an unknown resistance. So these values has been set according to table 5.1 for this simulation. So as you can see here, this is the table 5.1, which shows parameters of Wheatstone bridge. Okay, so this is the simulation that we did using Proteus software. So as you can see, based on the table 5.1, we have set the element values according to the table. So let's we run this simulation and have a look on what will happen. So as you can see, this is a variable register. So as we adjust this variable register, the microamperage or the current reading in the DC ammeter is decreasing or increasing. So it's depend on how we vary the resistor. So for this simulation, we need to make sure that the ammeter reading is near to 0 microampere. So let's we adjust that. So as you can see, when we increase the resistance voltage, so the value of the current is also decreasing. So let's go straight to the 0. Okay, so as you can see, we cannot achieve the 0 value according to this parameter setting based on table 5.1. So as you can see, the ammeter reading shows 0.41 microampere, which is the nearest to the 0. So the value of resistance that we got is 25.5 kilo ohm. So according to table 5.2, so this is the value that we have obtained from the simulation, and the ammeter reading is 0.41 microampere. So this is the formula that we have used for this calculation in order to find the unknown resistance, which is Rx equals to R2 times R3 over R1. So based on these values, we have obtained the calculation, the unknown resistance value, which is 6.6 kilo ohm. So based on the calculation, so let's we substitute the value of the unknown resistance, which is 6.6 kilo ohm, into the simulation. So let's we run this simulation again. So as you can see, we obtained a negative 35.9 microampere. So we need to adjust this variable register. So let's just make it to 100. So for this changed value in unknown register, which is 6.6 kilo ohm, with the usage of R3, which is a 100% capacity, so which is 30k. So based on this, so we can say that when we use the calculated values into the simulation, we obtain 0 microampere in the simulation. So let's we look into the step 5 for this activity 1, which is the simulation procedure, which is repeated for resistance R4 for a resistance value in the range of 500 ohm until 100 kilo ohm. So we need to set and record all the parameters in table 5.3. So for this Wheatstone bridge for an unknown resistance, so we have chosen 1043 ohm as our unknown resistance value. So now we are back into the simulation again. So let's we change this value according to the table 5.3. So for resistor 1 we have set into 9.7 kilo ohm. So for resistor 2 is same 2.2 kilo ohm. For resistor 3 the maximum value that we have set according to the table is 5 kilo ohm. For unknown resistance we need to change this value into 1043 ohm. So for this DC source we have set the value into 10 volt. So let's we run this simulation and we check out the result. Okay, when the R3 is in 100% usage, so the value shown in the current reading, which is 46.2 microampere. So we need to vary this R3 resistance. So let's we look into what happened when we adjusted this R3. So we need to make sure that the current reading is near to 0. Okay, so as you can see, this is the nearest value to the 0. So let's we look into the calculation. So the formula is the same. So we just substitute the value, the data from the table 5.3 into this equation, and we have obtained the unknown resistance value of 1134.02 ohm. Based on the calculation and the simulation, the value that we have obtained for the simulation is 0 microampere. So what we can say, so based on the result, the Wheatstone bridge simulation based on calculated value is more balanced compared to the Wheatstone bridge simulation based on the tabulated data. So with the correct resistance value assigned to each resistor and the range of these resistor values are same, when the voltage of nodes A and B are equal, the potentiometer reading will be 0. So that's all from me. So I would like to pass this presentation to my teammate. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad ZAKARIA. Will present about the activity 2, determining an unknown resistor using Kelvin Double bridge. First, we need to switch the voltage source and switch on the port. Then keep the switch S to short mode, switch K to open mode. Then adjust emitter to ampere. Then record the value of RS in the table 5.4. And after that, switch S swap to bridge mode and switch K to open mode. Set the value of RA and RA small to 1000 ohm. RB and RB small also to 1000 ohm from the control box. Then observe the value and millivoltmeter pointer and record it. record in the table below. Now set switch K to close mode. This switch K to close mode. Keep the RA and RA small to 1000 ohm. Vary the values of RB and RB small to RB to 961.3 ohm, RB to 999 ohm. Directly adjust the values in whiteboard to get a zero deflection on millivoltmeter pointer. When zero deflection is achieved, click on the calculate to observe the calculated value of unknown resistance. Then on the resistance value, we get 0.01. Then place the value to the table 5.4. Alright, after that, we repeat the procedure of Wheatstone lab to get the unknown low resistance. We use the low resistance between 0.01 ohm until 0.09 ohm. Then after we calculate it, we get the unknown resistance 0.02 ohm. Alright, that's all from me. Thank you.
For the activity 3, we have 6 questions. For the first question is explain the all result in activity 1 and activity 2 respectively. On the activity 1, we were using Wheatstone bridge. The result for the manual calculation and the simulation calculation had different results and it affected all the other parameters such as current and etc. On activity 2, we were using the Kelvin Double bridge. The result for the manual calculation and simulation had slightly different value on the decimal point. Somehow these differences doesn't affect the other parameter much. On the second question is discuss the simulation and calculation value of resistance using balanced Wheatstone bridge and Kelvin Double bridge respectively. On the activity 1, we were using Wheatstone bridge to find the unknown resistor. The R3 were adjusted to get the nearest 0 microampere. Unfortunately, we get the 0.41 microampere for 25.5 kilo ohm on resistor 3. Then the manual calculation for unknown resistance and the simulation calculation had slightly different result due to the percentage used on resistor 3. On activity 2, we were using the Kelvin double bridge to find the unknown resistor. The result on both simulation and the manual calculation are similar, it just has the slightest difference on the decimal point. For the question 3, we have justify the percentage error for the resistance measurement using balanced Wheatstone bridge and Kelvin double bridge respectively. Here we have the formula, and for the activity 1, the percentage error are around 8%, and for the activity 2, the percentage error are around 0.5%. For the question number 4 is differentiate between the accuracy of Wheatstone bridge and Kelvin double bridge for the respective resistance measurement. Because of the resistance is obtained using the null approach and it based on Kirchhoff's law, a Wheatstone bridge is more accurate than other resistance measurement method. The null point is the null method is unaffected by the galvanometer resistance and the cell internal resistance. The current through the galvanometer drops to 0 if one or more of the 4 resistance is altered. The null point is a term used to describe a point that is neither positive nor negative. The Wheatstone bridge is believed to be balanced when it is in this state. The unknown resistance value can be obtained from the two arms of Kelvin double bridge. Typically, it measures 1 to 0.00001 ohm with an accuracy plus minus 0.05% to plus minus 0.2%. Next one is question 5. Signify the bridge to be used for measurement of the test resistor having a value around 5 kilo ohms. We will use the Wheatstone bridge because Wheatstone bridge balance circuit to measure resistor larger than or equal to 1 ohm, whereas Kelvin Double bridge is modified version of Wheatstone that measure lower resistance value in the range of 1 to 0.00001 ohm. For the question number 6 is, in contrast, the unbalanced Wheatstone is often used for the measurement of different physical quantities. Determine the condition for unbalanced Wheatstone bridge. The voltage across the output terminal is 0 volt when the bridge is balanced. However, depending on the direction of unbalance, the output voltage of the bridge might be either positive or negative. And 6.2, we have state and briefly explain what is physical quantities can be measured using unbalanced bridge. Wheatstone is considered to be unbalanced bridge is V out in the above circuit is not equal to 0. The unbalanced Wheatstone bridge is commonly used to test many physical parameters such as pressure, temperature, strain, and etc. For the conclusion is there are different ways to measure using DC bridge. Impedance measuring bridge can be used to take accurate resistance measurement to the test different type of resistance and impedance. There are a number of bridges that are usually known by their inventor name. The Wheatstone bridge is a basic bridge circuit that can be used to detect medium range resistance because the impedance to be employed are actually DC voltage source and DC meter can be used. The Kelvin Double bridge is a variant of the Wheatstone bridge that considerably improve the accuracy of low value resistance measurement, often below 1 ohm. Thank you.